So I'm going to share screen now. Okay. Okay, so now I'm connected. Okay, so right now we ended up with trying to prove that this condition called acyclicity was an implication of utility maximization, right? So I asked you to try to do it. Of course, it wasn't an assignment, but we're going to try to prove it right now, okay? So I'm going to ask right now, let's see. I'm going to check the list of participants. Someone that hasn't done it. Maybe can Angyan please tell us now we're item 5, you can see, right? So can you hear me, Angyan? Okay, so now it's not connected. Okay, so then I will continue with Evan. So Evan, can you hear me?
Yeah, I can.
Okay. So
Yeah.
item 5, so it says if there is a unique solution to the UMP, it follows that if you have a chain of these direct revelations, right, then it has to be that the first item in this chain is different from the last item, okay?
Yeah.
So I'm going to write it in a slightly different way as well, right? So equivalently, if I have this chain of revelation, then it cannot be that xn is now strictly reveal preferred to x1, right?
Yeah.
Okay.
So I didn't do like a full formal proof, but I kind of just thought through it. And the way that I started is basically by contradiction, is kind of what I was thinking.
Okay.
So starting by supposing that x1 could equal xn, right? And then moving from there, just with the transitivity, we can find that, right, with the reveal preferred to from x1, like this chain, we can find that x1 is revealed preferred to xn. Sort of, we can.
Yeah, that's correct. So if this happens, right, then if the utility maximization, right, it has to be that u of x1 is greater than or equal than u of x2. Okay. Right? So right now we're saying that x1 is equal to, so if now, of course, by transitivity, right, of the real order, is equal to u of xn, right? So that means that, it has to be greater than equal. Now we have the key component here of this statement is that you have a unique solution, right? So instead of having these weak inequalities, we have to have strict inequalities, right? So there is only the top item. There is nothing on the difference curve. Just one point in the tangent. So so we have this thing, right? By the uniqueness of the solution assumption, we strengthen the inequalities, the weak inequalities to strong inequalities. And conclude that u of x1 is strictly greater than u of x. And now, this, of course, this contradicts the assumption that x1 is equal to xn, okay? So it's proof. So, so two things, right? So what happens, for instance, if I allow multiple solutions? Then what is the implication? So this is going to tell me that if you have this chain, right, then it has to be that everything is indifferent to each other, right? So, so the only kind of cycles that are allowed are weak cycles, indifference type, okay? But if you have unique solutions, then there is no cycles at all, okay? With unique solutions, okay, that's the difference. Now, so we know this is cyclicity, right? But actually has a name. So this name is usually called the strong axiom of real preference. I'm gonna call it here. Okay. So the weak axiom is only ruling out cycles of size 2. Okay. And the strong axiom is ruling out cycles of what size? Of any size, right? So size 2, size 3, size 4, until what is the maximum length of cycles that you can have in this data? Who has a clue?
N?
What is the maximum length of a cycle that you can have in a given data set of size T, capital T? So what I'm saying is, imagine you have a data set, right? So this is an experiment. In each experiment, an observation is a price and a consumption bundle, okay? So the weak axiom, right, is means that you cannot have cycles of size 2, right? So that means in a data set of size 2, you can just verify the weak axiom, right? Now, you need a data set of size 3 to verify separately the strong axiom and the weak axiom, right? Because you need at least 3 observations to have a maximum length of cycle of size 3. So if you find a cycle of size 3, then you have a violation of rationality, okay? So what I say is very important. So we're deriving these implications now. And these implications are actually testable implications, okay? So right now you can run an experiment. You can give people money and then present them with a budget constraint and then ask them for them to pick items in the budget, and then you will be able to tell me whether they satisfy the axiom of the weak axiom of real preference, right? And what I ask you is that so the maximum length of cycles you can observe in a data set is the size of the data set, right? So you need at least 3 points to reject the strong axiom, observing a cycle of size 3, and then you need a data set of size 2 to reject the weak axiom. So now I'm going to use the blackboard, right? Let me do something quickly. So imagine I propose the following experiment. So I have the same x2, x1, right? And then I give you a budget constraint P1, okay? And then let me do another one, P2, okay? Now say that in P1, the consumer chooses X1, right? And in P2, the consumer chooses X2. Okay? So this is an experiment, right? I gave you some money. The prices represent how much you can exchange from each of these two goods, right? Relative prices, the slope. And now you observe the experimental subject picking these two bundles, okay? X1 and X2. So can you tell me whether this experimental subject is consistent with utility maximization?
It is not.
It is not. Okay, Brice. So tell me why.
Because if you let the WAP,
Okay, so using the graph, right? So it means that in particular, right?
Mhm.
This thing here, right, is in budget P1. Okay. Now that means that this thing is below the line of the budget line P1, right? So that means that X1 is revealed preferred to
X2.
X2. But now I do the same reasoning for the budget 2, right? So what happens with budget 2? Right? And in fact, this second thing is strict, right? So this, because it's strictly below. So you have a violation, right? And so what is cool about this is that, you don't need, so you can now tell me exactly that this subject cannot come from utility maximization. Okay? This is actually very cool because originally, right, when utility maximization was invented, a lot of people said, and until now I have read this blog post of hobbyists of econ, right, that said, oh, utility maximization is not a real scientific theory because it's not testable. Well, it's actually testable, right? I agree that theories that are not testable in finite time, right, with finite data, they are not scientific. Okay, that's fine. That statement is correct, right? What is incorrect is thinking that utility maximization, because it's based on an object which is unobserved by nature, right, is not a testable, unscientific theory, right? In fact, it is. Now, and in fact, I'm telling you already, right? So people have run these experiments. I'm going to show you later in the class some experiments that were run under this idea, and you can test this thing, okay? Now, initially, when people invented utility maximization, they say, look, the best we can do is just fix a parametric utility function like the Cobb-Douglas, right? And then try to see the fit using some regression thing and say, oh, is it good or not, right? So this is like prehistory, right? You don't need to, right? You just need to check the finite experiment and check these conditions of the weak and the strong axiom and the weak axiom, okay? So the interesting thing about this is just with 2 points, I know for sure this cannot come from utility maximization. You see? So there is no way this thing can come from utility maximization. Now, imagine I have a new data. So everyone understands what's going on, right? So what I'm doing is I start with my theory, right? And as any theory, it has some implications that are testable on data. Okay, so I'm giving you 2 implications. Well, give you many. The first one is Walras law, which is not a great implication, right? You have to live on the budget line. The second one is homogeneity of degree 0. This is testable, but it's hard to test because you'll have to give you just this. So even in this kind of graphical device, I will never be able to show it, right? It has to be other interfaces. I have to give you like numerical prices and numerical income, right? And then I have to, change it with these constants and so on, and you can test it. Nobody has tested, it's not that interesting. Maybe it's interesting, but I haven't seen experiments for that one. But people have tested warp and the strong axiom, right? And the one famous way to do it is using these budget lines, okay? So they give you a budget line with an income and they tell you, oh, look, choose between this portfolio between 2 states of the world. And they give you probabilities of the states of the world. And then you can pick one, okay? So if you see a subject picking these 2 bundles, then it cannot be rational, okay? And that's very remarkable because you don't need like infinite data. You don't need really expensive collection of data. You just need 2 points. Now, of course, this is simpler than it sounds because I'm going to give you a different example.
Sorry, I just had one question. Can you just briefly re-explain how you got back to the reasoning of like with those budget constraints, how like X1 is real preferred to X2?
Yeah. So X1 is on budget P1, right? And then X2 is affordable according to that budget. So you could purchase it, right? It's just cheaper.
Yeah.
According to price 1. So therefore that means X1 is real preferred to X2.
Mm-hmm.
Okay, but then at the same time, X2 is on the budget line too, but then X1 is below it, right?
Yeah.
So that means it's actually strongly affordable. So it's even cheaper, right? You can save money buying it. So what's going on with this consumer? So this consumer first picks x1 over x2, and then now suddenly likes more x2 over x1, right? So now at prices 2, x1, that is the item these consumers show preference for, reveal preference, right? Now is cheaper, and however is not pick, right?
Okay.
Okay, so it cannot be rational. So rationality is about the stability, right? So this will imply that you are breaking just this idea that 2 is greater than 1, and then you're saying 1 is greater than 2, right? This is what's happening here, okay? So now, imagine I have the following different data set. So is this data set consistent with utility maximization? What do you think, Nico?
Yes, because for P1, the budget, like X1 lies on the budget line, and so X2 is unaffordable. But then for P2, X2 also lies on the budget line, and X1 is affordable, but he still chooses X2, so X2 would be preferred over X1.
Okay, perfect. Yeah, that's the correct reasoning. Now, one interesting thing about this particular data set is that it's a trick data set. So imagine I change it to any other. So I move X1 to any other position, right? Is still, I'm gonna claim is still rational, right? And in fact, I can move X2 to any other position and it's still rational, right? So what's going on? So this data set pretty much is always going to be rationalized by a utility function, because what's happening is that this experiment has no power to detect violations of rationality. That's the technical name, but what it means is that you need actually budget lines to intersect in order to be able to test rationality, right? So if you have just parallel budget lines, then there is no way to say whether in fact you are rational or not. So that means that, for instance, if the work consisted of parallel budget lines, so if only income is changing, right, not prices, then you cannot test rationality. You see what I'm saying? So if I run an experiment by just giving you more money, or you cannot test rationality, okay? Understood? Yeah, so this, what I'm telling you is that, you know, being testable is nice, so you become a scientific theory, right? That's nice. But at the same time, one thing is having an experiment that has enough you know, experimental power to detect violations. So it's a meaningful experiment, right? That's another thing. So the fact that you pass certain data sets pass rationality, that is not really a strong evidence in favor, right? It's just that the theory is not rejected. So the idea in scientific theories is that if you falsify it by observing a violations of it, then you're done with the theory, right? The theory doesn't work anymore, right? But if you find a data set which is consistent with the theory, then you know that for now it hasn't been rejected, right? So far for this particular data is a good description, but I cannot really extrapolate that much, okay? So the other way, like when you find support for a data set, is really always weaker, because you can always add more experiments and so on, and eventually, you know, the way to do properly will be to run a large amount of experiments, right? And eventually the theory is still good, then you will still use it, okay? Do you understand? Okay, good. So, so I'm gonna share back the links. So now, let's compare this with chapter 2. So chapter 2 tells you that we are using the Samuelson idea. We were kind of free of models, free of utility. And Samuelson idea was saying, look, we can do predictions in terms of demand just using these consistency conditions, right? And Samuelson proposed this weak axiom or real preference as the minimal condition. He said, look, we're gonna do predictions using just the weak axiom, right? And I don't need utility anymore. Now, the other branch of this literature is saying, look, utilities are useful for modeling, right? They are a nice mathematical device to be able to capture, you know, intention of agents, and you know, we can do a lot of things with utility, right? So many economic models that start with maximizing some utility function, right? Models of crime, models of job search, models of marriage markets has a utility in the middle, right? And you're maximizing it. So now, if you're using that kind of model, the first finding, and this is the classical finding in the time of Samuelson, was that by maximizing the utility function, you always get the weak axiom, okay? So it turns out that the two approaches are not that different, right? Because both have a point of convergence in the weak axiom. If you are utility maximizer, you imply the weak axiom, right? And therefore, they at least have this consistency condition that Samuelson said it was good. Now, what happens with the strong axiom? So the strong axiom is important because it's telling you that utility maximization is in fact implying something more than the weak axiom. So it's not the only the weak axiom alone, it's more than it. So it's giving you this acyclicity condition. Now, so we did a new theory of behavior, now using utility functions, which are complete and transitive. And preferences and utilities are not observable, right? Do you understand that? So they are mathematical devices that serve to capture some idea that theories have about behavior, but they are not testable. So I cannot see your preferences. I cannot see your utility directly. So I have to understand what is the implications of maximizing preferences with certain properties in terms of my particular environment. And I derived this big implication, which is called the strong axiom of real preference, acyclicity, okay? So now acyclicity, surprisingly, I haven't proved it today, is all the implications possible from the utility maximization model. So there is no more implication. That's it, right? So warp is a special case of acyclicity. Acyclicity is exhaustive. So it is the whole empirical content of utility maximization. Okay, so now that's actually cool because you can now judge how sensible the theory is by using this condition, right? So let's evaluate the theory in two layers. The first one, which is more for fun, philosophically speaking, is, do you think it's a sensible model of behavior just by introspection, right? So we're humans. Do you think this is something you can follow as a rule when choosing? Do you think it's something you follow? So the weak axiom is a little bit simpler, right? This is about the law of demand, right? So prices goes up, quantities goes down. I pick something when another thing is affordable. If I have a new situation, I won't flip my preferences, right? No flipping condition. But here, so do you think this is sensible, sorry? So this is a matter of opinion. So what do you think? So this is kind of related to transitivity, right? But in reality, so the question is, do I want it, right? And the cool thing about this particular step that we have given is that we have derived all the possible implications of rationality. So we now know that it's not just warp, as Samuelson wanted, but this deeper layer. Okay? So again, the real test of any theory is doing it with data, right? So people have done it, and then we have checked whether this condition holds. And the evidence so far is kind of mixed, so I'm going to give you more later in the course. But bear in mind that the key innovation for now, what you have to remember, is that even if this theory is done in terms of something that is not observable, we can derive implications that are testable, right? And allow us to judge the theory in a more transparent way, okay? This is the take-home message at this stage. So now, what about the Zlotowski matrix? So in the chapter 2, we derived this Zlotowski matrix object. And now I'm going to tell you the following theorem without a proof at this stage. And basically, we're going to understand this in the main course, in the main class. But right now, I'm going to give you some connections with the Zlotowski matrix. So a demand function X that satisfies Walras law is differentiable and can pretty much can be generated by the utility maximization problem. So a demand function comes from maximizing a utility function. if and only if it's a Zlotsky matrix. Remember from chapter 2, the Zlotsky matrix is not connected to the utility itself, but to the demand, right? So my object of this, the starting point is demand. I compute the Zlotsky matrix. If the demand function came from maximizing a utility function, then the Zlotsky matrix is actually negative semi-definite. This shouldn't be surprising, right? If it satisfies warp, then it should be also negative semi-definite, right? But there is a new property suddenly, and it's symmetric, okay? So this you did in the problem set, right? So you derive the Zlotsky matrix of the CES, and you verify that the Zlotsky matrix is symmetric, right? But why? Why is symmetric, right? So the reason why it's symmetric is actually going to be related to the fact that it's utility maximization, right? So, and in fact, is also a manifestation of this acyclicity, okay? So the connections of these three objects, of course, are not obvious, are hard, even mathematically hard. But we're going to understand one way of why the Zlotsky matrix is symmetric, okay? So let's proceed. So before that, I need some preliminaries, and I also am going to introduce some additional objects of interest. The first one is what is called the indirect utility, okay? I'm going to use all of this in a bit. An indirect utility is a simple object that is the maximized value of the utility. So it's evaluating the U at the optimal demand, okay? So you maximize, you obtain the XPW, and you replace it in the U, you obtain the indirect utility. The indirect utility now is the value of the welfare you obtain at the particular price and income level, okay? So for a given price and income level, it gives you how much utility you experience, okay, for the particular fixed U. And now I'm gonna have some, of course, some properties of it. And the first one, these are consequences of the properties of demand. So is homogeneous of degree 0? Yeah, because the demand itself is homogeneous of degree 0, right? So that's fine. Is strictly increasing in income and not increasing in prices. So this is telling me that as income increases, you're gonna get better off, right? So proving this is gonna be done in the main class, but you can see it's very intuitive, right? So what you're doing is relaxing the constraint, and you are pretty much making it less restrictive. So therefore, you're gonna be able, due to local non-association, you can only improve, right? So you can only improve due to local non-association, and it's gonna be increasing always. And not increasing in prices, okay? So of course, there might be some particular prices which doesn't improve you strictly, depending on the utility, right? For instance, think of a utility of two goods where you only care about the first good, right? So that's an example. And then the other properties are more technical. This one here is just almost a definition right now. I'm not gonna prove it. It's gonna be more meaningful in a second. But it just means that the fact that you utility maximize is going to give some structure to the set of objects, price and income, that are the objects that are below a certain target level of utility. So this is going to come handy in a bit, but right now it's just a property I'm going to state. There is nothing meaningful. I'm not going to prove it either in this summer bootcamp. And finally, it's continuous. Okay. Continuity is kind of interesting and is important because this follows from something you're going to learn with Maria, which is called the maximum or Berg's theorem, okay? So if you're maximizing a continuous objective in a continuous correspondence, which is the budget correspondence, then the value function is going to be continuous, okay? So we get this for that. So continuity is important in that sense. Okay, so now, why do I care about the indirect utility? So the indirect utility turns out to be a capsule containing all information you need about behavior. Okay, so and this is the next thing I'm gonna tell you. So this is called the Roy's identity. And I'm gonna introduce something very quickly. I'm not gonna explain at this stage. Also, you learn it usually in the math class, but this is something you should know already, but you can also, Google it and so on. It's called the envelopes theorem, right? And this theorem is telling you how the objective value changes when I change parameters of the problem. And the key thing is that now I'm dealing with a constraint problem, right? So the envelopes theorem is telling me something very nice, which is that I can understand how welfare or indirect utility changes with respect to parameter price and parameter income by taking the Lagrangian and assuming the x is constant, and then just deriving with respect to the parameters. So why this is almost like magic, and I want you to understand and appreciate it, right? This thing. So if you're dealing with a constraint problem, right? And I want to understand how the objective changes with changes in the parameters of interest, right? So then what do I have to do? Well, imagine that I change income, right? Which is the easy one to visualize. So I have to go modify the constraint, right? Compute again the optimal value, and then compare with the previous optimal value. So I have to do, you know, several optimizations, right? And then for all levels of income. And then of course, locally, I check the difference and I tell you the answer. Well, so the envelopes theorem, which I'm not proving, but I'm stating, is telling you, you don't need to do that. You know, it's actually very simple. Just state the Lagrangian and then take the x, which is the value that I'm optimizing over, right? As if it was constant, okay? And then just derive with respect to the parameters given that constraint. So imagine now that I want to understand how the welfare changes with changes in income. So I go to the Lagrangian, I assume the x is constant, and then my derivative is going to give me lambda. Okay, do you agree? So lambda makes a lot of sense, right? This is the multiplier. Remember, it was a positive quantity, right? And this is called usually the shadow price, because this is telling you in usual optimization theory, because this is telling you the value of relaxing constraints. But for us, for econ, this is called basically the marginal utility of income. Do you see why? Because it's exactly that, right? So it's the marginal change in utility, indirect utility, with respect to a change on income, okay? So lambda is capturing this change in the parameter. So now lambda, of course, the one I'm talking here, is the optimized value. So remember, lambda is one of the unknowns in the Lagrangian problem. So this lambda is a constant lambda, right? Is the optimized value of lambda. It's not a variable Lagrangian. Is already an optimized value, okay? And then the one that is more important is the derivative of the welfare with respect to prices, okay? So now, again, using the same logic, turns out that the solution is just minus lambda, which is a constant, times x, which is a vector, okay? So this notation here is the notation of a gradient. So what is a gradient? Well, a gradient is just the column vector of partials of the indirect utility with respect to each price, right? So entry L is with respect to price L. Do you understand? So this here is a column vector of size L1. This here is a column vector of size L1. And then lambda is a constant, okay? So this is telling me that how welfare changes with respect to changes in prices is proportional to the marginal utility of income and times the quantity. It makes a lot of sense, right? Because the lambda, what are the units of lambda? The units of lambda are basically telling me utils, right? With respect to quantities, right? So what is x in what units? In units of quantities, right? So then, of course, what are the units of this expression? Utility, right? Utils. So what this lambda is doing is transforming quantities into utils, right? So what is the change in terms of prices? You know, whatever you purchase times the marginal utility, okay, of income. So that's kind of cool, and this already proves these properties here, that BP is strictly increasing in W and not increasing in PL. Why is it strictly increasing in W? Because lambda is strictly positive, and not increasing in PL because X may be zero, right? The quantity may be zero. So now, combining them, I actually can invert this thing, right? And show that demand is equal to this gradient, which is a vector, right? Divided by a scalar. So the division here stands for entry by entry division by the scalar object in the denominator, okay? Do you understand? So, and with a minus. And this is a lot of information. I want you to understand that this is telling me that utility maximization, if you think about of this as a theory thinking of this more than a statistical theory, if you want, in the sense that I'm going to use it for estimating demand, for instance. Right now, there is nothing statistical or probabilistic about this theory. I'm telling you right now, eventually, I will use this kind of results to be able to estimate demand, okay? So in short, what I want you to realize here is the dimensionality of the two objects in the left and in the right. What is the dimensionality of the object of the left, which is the demand function? Is a column vector of size L, okay? So imagine you have many, many goods. Imagine you have hundreds of goods, okay? So this vector can be potentially large. Now, what is the dimensionality of the object on the right-hand side? Well, it's of the same dimension, right? But it's actually coming from a scalar object, the indirect utility, you see? So we're actually we're wrapping all the information into a scalar object, the indirect utility, size 1, okay? And then through derivation, I'm getting the full dimension, okay? So again, utility maximization is reduction of dimensionality, and very, very actually, a very, very strong form of reduction of dimensionality. Because imagine you have hundreds of goods, you're gonna tell me that in a scalar object, all the information about this demand is going to be contained. So now, let's imagine the following problem. So tomorrow you're gonna be interviewed to work in Amazon, right? Which may happen. And I'm telling you the following problem. So I'm gonna give you a data set where you observe prices and you observe consumption at that given price, okay? Consumption is a vector of things, right? Think groceries. People are buying groceries now online. So it's a vector of groceries, okay? So produce, vegetables and so on. This is a vector of size 2 for simplification. Now, you observe prices and you see what these people purchase, okay? And in fact, this vector actually is of size, say 100, as I mentioned before. Okay, so then I tell you, okay, I want you to write down a model of purchases, right? I want you to model how quantities change in terms of prices, and just for simplification, in terms of prices, right? Fixed income to a fixed level, 100, right? So we're not thinking about income right now. So what will you do? So what model would you use? So anyone among you has some experience doing any empirical model? Has anyone done anything related to demand? Some of you have already seen what is a linear model, right? So at least, tell me your best shot. Okay, so maybe Feng-Fan.
Can you speak the questions again?
Yeah, so I want you to model pretty much a model of demand. So say I give you data on prices and data on consumption, okay? So imagine you have a vector of consumption that is of dimension 100. So you have 100 goods, okay? And then your independent variable is prices. So you have 100 vector of prices, right? So you have prices for the 100 goods. And that's your data set, right? So you want, what would you do, right? Imagine income now is not an issue, it's constant. So your task is to model it. So tell me, describe simply, what would you do to model this vector? This is a statistical model right now, if you want, a mathematical model. How will you model it?
I mean, you can use some simple regression.
Okay, regression. So that means what? So in order to do a regression, you're telling me a lot of information, right? So let's go to this thing here. So you have here consumption of L, right? And now you're telling me a regression. So alpha 0, right? Alpha 1, P1, alpha 2, P2, dot, alpha 100, P100, right? And now this is good L, right? So this elasticity is maybe heterogeneous with respect to each L, right? So that's a linear model, right? It of course has some issues because it can be, for instance, maybe it's not linear, right? All these issues and so on. So, but right now we're not gonna focus on that, okay? What I want you to understand is how many of these equations do I have? So I have right now 100 plus 1 parameters per L, right? Okay, so because we say L was actually 100 as well, so it's 100 times 100 times 1, right? So how many parameters do I have now? A lot, right? It's 100 times 100, right? Do you understand what is the issue here? So we have many, many parameters. Yes, Brice, so you said something, I think you were mute.
Yeah, I mean dimensionality issue.
Yeah. So now, what do you do? Well, of course, now you're a machine learning guy. You will say, "Oh, let's do, model selection, right? Some lasso technique, something like that, to reduce dimensionality." Okay, but that's kind of brute force reduction of dimensionality, right? Like the way you do it in science is by creating a theory, right? So a theory essentially is reducing dimensionality, right? That's the purpose of a theory. So now I'm gonna write a theory, right? So I'm gonna say, look, now this vector of, I know, L times 1 is the maximizer, right? Of some utility and so on, subject to a budget, okay? Income, I'm gonna fix it to 1. So this is the model I know, but how does it help us? Well, let's use Roy's identity, okay? So right now, I'm gonna just model the indirect utility, okay? So I'm gonna write the indirect utility of prices. Now there is no income, remember income is 1. It's gonna be what? It's gonna be now alpha 0 plus alpha 1 of a quadratic term. So I'm gonna call it this P times, so let me do it a simpler way. Let's say this is price of good 1, right? And this is elevated to the square, and this is alpha term, alpha 1, and then you have alpha 2 P1, and then plus dot, dot, dot. All these terms are gonna enter with the quadratic and the linear term, okay? So I'm gonna have alpha L, the term that I'm gonna call the quadratic term with a line, and this is P100 2 plus alpha L P100, okay? So I just wrote a quadratic model for the indirect utility, okay? So this has a constant and then has a quadratic term and a linear term, okay? So how many parameters do I have now? So I have a constant, I have 100 terms from the quadratic terms and 100 terms of the linear terms, okay? So I have 201, right? But it's less than 100 times 100, 100 times 100, right? It's way less, okay? So now what do I do with this? Okay, so how do I go from this to a demand function? Who can tell me? Sorry, I didn't hear you.
You can use Roy's identity.
Yeah, the Roy's identity, right? So now I don't have income, right? So I know that X, the XL, right, is equal to the partial of V, right? It depends on all the prices, P1, P2, P100. With respect to L, okay? So in particular, this one, if I derive it, right, is going to be 2 alpha L, right, times P plus alpha L. And this is of good L. Okay? So this model is actually very simple, right? It's only depends on its down price and has a constant. That's it, right? Okay, so this model maybe is not the best model, right? It's maybe too simple. I need maybe some interactions to have some cross substitution effects. But I illustrate my point, right? My point is that having a utility maximizing model reduces dimensionality substantially, right? And Roy's identity, and way to understand the usefulness is that instead of modeling demand in a very arbitrary way, dimension by dimension, which can get very daunting very easily, 100 goods, 1,000 goods, right? You can just focus on modeling the utility. And now you understand why utility maximization is so popular, because basically all these complex problems, criminality, buying houses, marriage markets, finance, macro, and so on, can be reduced to a scalar object, right? And then, you know, the work of economists is getting creative to try to see that this scalar object and modeling is actually rich enough to capture some phenomena in the data. You understand? Now, and now you can see what is the current discussion between machine learning and science, right? What is better, econ or machine learning? Why are you here instead of computer science? Why are you here? Because they pay better. Not just kidding. But you know, this thing is not done, right? Right now they are winning, but it's really a matter of time. So the issue is the following, right? So what is the key of a scientific theory? I told you a moment ago, right? Scientific theories have to be testable, okay? Why do I care? Beyond, you know, beyond the principle, right? The principle that this is science. I care because by being testable, it's equivalent to saying that I'm able to make predictions, okay? So to understand that, imagine you have a theory that is not testable. What does it mean to be non-testable? It means that I can always explain any data set that you give me, okay? That sounds great, right? But that has a caveat. I can only explain data in sample data. So whatever data you give me, I'm gonna overfeed it. I'm gonna create some very weird model, right, in my non-testable theory to be able to fit exactly the data you give me. But now the issue comes when I give you an out of sample point, right? So the whole point, the whole idea of doing models is to be able to predict. If I overfit some data, I can never predict, right? Because the theory is too general that everything goes. So you give me a new point and you say, oh, well, everything goes. But I can retrain the model to be able to feed it again. That's not prediction. That's not how it works, right? You understand? So the key idea of science, which is what people are forgetting, is that prediction requires understanding. Prediction requires reduction of dimensionality, okay? So if you don't have that, then everything goes. And in everything goes, there is no prediction possible, okay? So now with machine learning, you say, still people predict with machine learning. What's going on? Well, here's the deal, right? So a lot of machine learning prediction is done with the idea of continuity, right? So you hope that the out of sample points are very close enough to the in sample points, such that whatever you predict is kind of good, okay? But you know, this is always a promise, right? There is no guarantee that it's going to happen. So now, if you understand the mechanism, if you simplify it as a theory, and if you create a reduction of dimensionality, which is efficient enough to understand the main mechanism of a complex phenomenon, then prediction becomes more feasible, right? And that's basically our other extreme, physics, right? So you have this, the theory of relativity, which makes the prediction that if you check a solar eclipse, you're gonna see the curvature of light in a certain degree at a very, very high precise level, okay? And then people go measure it and you exactly get that, right? So the prediction hits it with, you know, a level of precision that is amazing and beyond our dreams in econ, okay? But that's not, of course, machine learning. You need intelligence, you need reduction of dimensionality, right? So you need to reduce forces to the minimal expressions, okay? So now in econ, we have both things competing, right? So, and the question is, what is the best mix? And what is happening right now is that a little bit these tools of machine learning are trying to create automatic theorizing, right? So imagine that, for instance, you were an experimental guy trying to check which are the main forces in a particular phenomenon, right? You have to think, you have to start abstracting, you have to be smart, right? To be able to pick the most important factors that explain your phenomenon, right? Now, machine learning, the promise is that you can use a lasso, for instance, which is pretty much an optimization problem that will automatically select the main predictors of a particular model, right? So in a way, you are reducing dimensionality by means of a machine kind of following a rule to be able to do it. But in the end, it's reduction of dimensionality. Both are the same, right? So which one is better? Well, right now, machines are still kind of stupid to define which is the good objective, right? They kind of work in simple cases. Humans are still better, right? But maybe machines become really smart and then they can actually do that, right? But really our hope, the only hope we have as humans is, I think, that particular case, right? So theorizing. If you can imagine, right, what a human can do is really about creativity and modeling. So you're not gonna be, you know, higher because you're really good at accounting, right? A machine will do it better than you because you're really good at arithmetic or at algebra. But the only advantage that we have, comparative advantage, is creativity, right? Trying to abstract and try to find the main forces and how to model things in a smart way. So utility maximization is an intellectual triumph and is really, really useful, right? Imagine all these applications that we have in the different fields of econ. So, you know, if you think of something as complex as crime, and most people, you know, even people in law, they have been discussing for centuries why people commit crimes, right? And then economists come, cynics as we are, and we write down a scalar object that says you commit a crime whenever the expected utility value of committing the crime is more than the probability of getting caught with the multiplied by this utility of getting in prison, right? So that's the magic of it, and also it's kind of dangerous because sometimes it's too simple. But for practical purposes, now you understand what's going on, right? So if you're modeling a demand system, right, the economists will write down a utility, and the machine learning guy will try to select these different 100 times 100 parameters using other techniques. You have two approaches, right? What is better? Well, Amazon has an economist team and a machine learning team, and they actually work together. So I don't think anyone has won yet, but they definitely have an advantage in the implementation and the empirics because they actually do it. Economists are still theorizing, right? But but the idea, I think, is actually still very useful. So again, places like Amazon, Uber, and so on, they use economists that use structural techniques to be able to model demand. So my point is that you have to understand that all these things we see actually are very useful, and people do use them, in fact, in real life, right? And the key idea why they are so useful is because they imply this super strong form of reduction of dimensionality. So you can reduce any problem to a scalar problem using a utility function. Of course, you pay a price, and the price you pay is you're implying this strong axiom of revealed preference. So not all things can be captured, okay? So let's continue, and I'm gonna give you something called the expenditure minimization problem. This is mainly important because this will serve us to understand the symmetry of the Kozlowski metrics and understand the limitations of this approach that economists have taken, okay? So expenditure minimization problem tells you a fictitious problem where you can imaginary fix a utility target, and you're asking the consumer minimize the amount of expenditure, money, prices times X, such that you at least get a minimum level of utility U bar, okay? So this problem here can be solved by Lagrangian methods as before. So I write down a Lagrangian problem. Now, as you can see, the objective is linear, P times X, and you have lambda minus the constraint. We're gonna assume interiority for simplicity, and you have the first order conditions, okay? Now, from this problem, there are two objects that are the product of the solution of this problem. The first is what is called the Hicksian demand. The Hicksian demand is the minimizer. So this is the demand that will hit the U bar level of utility at prices P. Okay, is a vector of size L times 1. And the value function, which is prices times the Hicksian demand, which is the expenditure at the minimized level. Okay, and with this object, I never see it. So why do I care? I'm gonna care because it has a dual relation with the object that I do observe, which is the demand function. And using that, I'm going to be able to derive this implication of symmetry of the Zlotowski matrix. Okay, so the first relation is that if I take the Hicksian demand and I replace the target utility by the indirect utility at the price and income level, PW, then I get back the original observable Marshallian demand. Okay, this is very easy to see because we have this dual relation, right? What is the target utility I'm targeting now? Is the maximized value of the UNP. So now, of course, spending the least amount of this is going to be equal to maximizing utility. So again, the proof is not done here. It's going to be done in the main class. This proof is anyway very trivial. And the second relation I have is that I can go back now from the Marshallian demand to the Hicksian demand. So here I change the income level to the expenditure that hits a particular U target. And this will give me the Hicksian. And the more important relation is this one here, which is that the target utility is equal to the indirect utility evaluated at the expenditure at the target utility. So that means mathematically that the indirect utility and the expenditure are inverses. So do you know what is an inverse function, right? So say you have x to the square just for the positive numbers. What is the inverse of x to the square, to the power of 2? Is the root square, right? So of course, for positive numbers. And what is the property of this? If I apply the inverse to the original function, I get x, right? So this is what is happening here. So I apply v to this expenditure function at the value u level. So if you fix prices, really what you're doing is inverting, right? So you're getting back the u bar, okay? So for fixed price, this is an inverse. And the same happens the other way. I mean, the argument, if I fix price, the argument is income. So I apply the expenditure to the indirect utility and I obtain income back. So the expenditure is the inverse of the indirect utility, okay? Now with this in hand, what I'm gonna do is I'm gonna give you some properties of the Hicksian, which again are very simple, and then I'm gonna use it to prove symmetry. So homogeneity of degree zero in prices. Well, in this case, if I change by alpha this object, then the maximizing value will be the same. Why? Because here the constraint is not changing, right? It's still the U bar. So you spend more money, but at the same quantities, okay? So you spend more because they're more expensive, but you still consume the same object, okay? Why this happens? Because all prices change in the same direction. So relative prices remain the same. The second one is that I actually hit the utility level, and this follows just from continuity. So the argument is very simple and very similar to the one that why we're in the Walras law in the previous case. So you have a contradiction if you are just below. So I'm not gonna do it right now. Under strict convexity, the Hicksian demand is unique. If you are not strictly convex, you're gonna have a set, okay? And in fact, this set is gonna be convex. That's another thing. The important thing that I want you to have now is that this, in number 3, this expenditure function happens to be a concave function. So what does it mean to have a concave function? Well, I'm gonna move to the board. So what is a concave function for one dimension? So this is a concave function, right? So you take a combination of 2 points in the image, right? And then this point is gonna be below to the particular one corresponding to this combination here, right? So this is a concave function. Now for multiple dimensions, concavity, I'm gonna give you the definition now. means that the expenditure, the function evaluated at the mixture of alpha price plus 1 minus alpha p prime, which is a second different price, is greater than equal than alpha of the original expenditure at prices p plus 1 minus alpha of the expenditure at price p prime. Okay? So why this is necessary instead of just the graphical representation? Because this works for multiple dimensions. So the example I give you is just when price is a scalar, right? But for multiple dimensions, you need a mathematical description. But in general, what you have is this kind of mountain-like behavior, right? So it's a mountain. Okay, so I'm going to define P alpha, which is this convex combination of alpha P plus 1 minus alpha P prime. So alpha is just a constant. And I define what is the expenditure function for that particular P alpha. So the expenditure function, I maximize it, I obtain the Hicksian, and then what is the Hicksian for P alpha is this particular H P alpha. And now multiplied by P alpha itself, it gives me expenditure at the P alpha level, okay? Now, this one here, by definition of P alpha is equal to alpha P times the H evaluated at P alpha, 1 minus alpha P prime. This is a transpose, so I have to use the same sign, the same symbol, is H of P alpha. Okay, good. So, what is the key idea that I'm gonna use now, right? Is that I have here that P times H P alpha is actually the expenditure of P, okay? So the expenditure is the minimal value attainable in terms of expenditure that hits the level U bar at prices P. So by definition, this quantity here has to be weakly above. Do you understand? Because the minimum value is the expenditure, right? So this is the minimizer. So any value that is not the minimizer, in particular the HP alpha, has to be slightly above. Well, maybe more than slightly, but it has to be weakly above. Got it? So because of this, now it has to be that this object here is greater than or equal than this first object here, and the second additive term here is also greater than or equal than the second additive term here. So together it means that this term here is greater than or equal than the convex combination of the expenditures, okay? So this is convex, this is the concave function, sorry, okay? Now, so you have a concave function, this is gonna come handy in a second. And now I use again envelopes theorem. So I'm gonna use what is called the Shepard's lemma. So which is again an application of the envelopes theorem, but for the case of the expenditure. So I apply it and I obtain that the gradient of expenditure with respect to price is equal to the Hicksian. So in this case, there is again reduction of dimensionality, but even simpler because you don't need income, okay? So utility is fixed. So I want to finish with these properties, and all of this will make sense in a second using the Zlotowski equation. So the first thing is, what happens if I take my vector, my system of equations, which is a vector, that is the Hicksian demand, and I obtain its matrix of substitution. Okay, so that means what is the size of this matrix? Is L times L. Got it? What is the typical entry? Is changes in Hicksian of good L with respect to changes in prices K, okay? Entry LK. So turns out, because of the Shepard's lemma, that this is equal to the Hessian of the expenditure. What is the Hessian of expenditure? So the Hessian is this matrix of partials, double partial, right? PK PL of expenditure. Okay, sorry, expenditure, scalar. Okay, so this object here, right, is the typical entry. Okay, so this is the Hessian, is the cross derivative. So two derivatives. Got it? Now, what do I do now? Well, first of all, a Hessian of a concave function is always negative semi-definite. Do you agree? So think for the scalar term. So if you have a scalar term that is a scalar function that is concave, what happens with its second derivative?
Less than 0.
Exactly, less than 0. So this is the multivariate version, okay? So you have a multivariate concave, so concave, and then you obtain the second derivative, the Hessian. And the Hessian is negative semi-definite, okay? Got it? And then the second term is that the Hessian actually is symmetric. So why is symmetric? Well, if you have cross derivatives, right? You have here that the partial of, let me write it here. Is equal to this thing here. Do you understand? So why these cross derivatives now can be changed? This is a theorem, right, from math, which is called the Young's theorem, that tells you that if the function is continuous, then you can exchange derivatives. Okay, calculus 3 in some chains. Okay, so okay, so now this thing here, because it's the Hessian, is symmetric. And then you have this singularity in prices, that this object here multiplied by price is equal to 0. So all of this looks like the Zlotski matrix, right? And in fact, this is going to be the basis of why the Zlotski matrix has the properties that I told you. And in order to do it, I have to use this duality condition. So first of all, I remember that the Higksian of PU is equal to the Marshallian XP, E PU. And if I differentiate with respect to P, I get that the substitution effect of the Marshallian plus the second term, because of the, remember that prices appear also here inside expenditure, right? So by the chain rule, I have the income effect here by the derivative of the expenditure. So now I use Shepard's lemma, and this part becomes what? The Higksian, right? The last term becomes the Higksian, okay? This is Shepard's lemma, right? What is the gradient of the expenditure? Is the Higksian. So now putting all of this together and replacing the fact that U can be replaced by the indirect utility BPW, now I get what's called the Zlotski matrix. So the Zlotski equation, sorry. So this is the Zlotski equation. So remember, this is not a matrix, this is an equivalence. Okay, Zlotski matrix is one object that you can compute from the demand, and this is Zlotski equation, which is an equivalence, right? So the equivalence between the Hessian, remember this is the Hessian of the expenditure, right? And this is the Zlotski matrix, which is observable. This I can compute from demand. So what does it mean? So wrapping up, it means that a demand function that comes from utility maximization will satisfy symmetry, negative semi-definiteness, and also this singularity in prices, right? So the fact that SPW multiplied by price is equal to 0. Okay? All of this comes from the expenditure function and the duality. Got it? So now, I did a lot of math. Getting the symmetry of the Zlotski matrix is actually really cool mathematically, but what is it telling me, right? So going back, you're in the interview with Amazon, you are telling the interviewer, look, I'm an economist, I'm gonna reduce dimensionality differently, right? Using an indirect utility polynomial. Now, you did that. And then the Amazon interviewer tells you, okay, but what is the catch? Yes, dimensionality is smaller, but you have to pay a price, right? There is nothing free, no free lunch. What price are you paying? Like in terms of the Zlotski metric, so think about it. So what is the end product for Amazon? Why do they care about demand? What is the object they are after? So why if you were in Amazon, why would you like to estimate demand? elasticities, right? So you can increase prices and see how much you can push the consumer, right? If you know, if I change price too much, maybe demand falls too much, right? So it's about pricing, okay? So elasticity is the key ingredient for your pricing model, okay? So everyone understands that. I'm after elasticities. What is an elasticity? You know, roughly is the unitless version of the derivative. What is the change in demand with respect to changes in prices, right? And then I do some normalizations to make it unit free, and that then becomes elasticity, right? But that's an elasticity. The percentage change in quantities with respect to the percentage change in prices. Okay, got it? So you want an elasticity, okay. So the interviewer says, okay, I want my elasticities. What is the cost of doing this reduction in dimensionality that you propose? So the model, obviously, what happens if you do a model that is lower dimensionality? It becomes more restrictive, right? That's obvious. So what is the nature of the restrictiveness? Can you tell me a precise answer? The Zlowski matrix is telling me the precise answer. Now think about it. So it has three implications. So it means for any model you estimate, no matter how general your polynomial is going to be from the indirect utility, you always are going to have these three properties, right? So symmetry, negative semi-definiteness, and this singularity in prices, okay? So for instance, let's think about negative semi-definiteness. So the interviewer says, you know, your model, right? If I want to defend this with interviewer, say, look, my model is going to imply that the larger the price change, the quantity is going to fall, okay? So that one is a nice property, right? I think most people are going to agree that if prices goes up, quantity goes down, at least in Amazon. So that, you know, is nice to have it. I know even that is restricting, right? So I'm avoiding overfitting to having some weird, you know, opposite sign object, right? So my structure is now disciplining the data to make it actually downward sloping. So that one is nice. And then how you do defend symmetry? So what does it mean to have symmetry? So think of the grocery example, right? So say you have produce versus meat. So now symmetry means that these substitution effects from the changes in consumption in meat with changes in price of produce has to be equal than the substitution effects of produce with respect to the price changes of meat. They have to be numerically the same. Do you understand? That's symmetry. Do you think that's good? Do you think that's bad? So tell me your opinion, Tyler.
Yeah. The first thing that comes to mind is either, well, I guess imperfect complements, but I'm not sure if that would be relevant.
Complementarity?
Mm-hmm.
Yeah, so complementarity is an issue in itself, right? Here, all this, so we have here that negative semi-definiteness means that everyone is a substitute, right? Weakly so. So yeah, that may be an issue. But in general, right? So the question about symmetry is really something is unexpected, right? So I don't think it's something defensible. I think it's actually a bug. So you have this weird behavior that tells you that, you know, this cross derivative behavior of the substitution effects is the same. I don't see why, right? So in this particular case, you hope this is like the Einstein part, right? So if this theory was actually really good, you will actually go to the Amazon data and then, you know, measure this Zlowski matrix, and then this is like the light bending near the eclipse, right? And if it happens to satisfy this amazing property of symmetry, then your theory is surprisingly correct, right? And then you have the Einstein of econ. That happened in econ. So people have tested this in many ways in many data sets, and usually it comes that it's not symmetric. So in the end, it's an empirical question. But what I want you to realize is that, so this is important why you have to understand these models, right? So the moment you say, I'm doing a utility maximization process, I'm doing a structural demand of behavior. So from utility maximization, I use Roy's identity, whatever you want, you obtain a model, and then, you know, you get a property that is kind of, nobody's gonna bother you much, which is the negative semi-definiteness, right? Law of demand. But then you get another property, which is the symmetry, that is actually restricting behavior in a weird way, okay? So this one is not a nice property, okay? So then, you know, you have to think, and this is what people currently are doing. So if you want to be taken serious, like more apply guys, you have to think of ways of how to relax this symmetry, okay? So you have to think of ways of extending this model to make it a little bit less restrictive. And, you know, what is the correct level of restrictiveness? Well, this is an art. So this is the game between theory and between data, right? So right now, it seems that utility maximization is, at least for consumption, is way too restrictive, okay? So too restrictive. It just implies this weird thing about symmetry that we don't want, okay? So yeah, but right now, as you can see, so is that these objects in the end by themselves, mathematically, they don't have any content that is normative. So they are not bad necessarily, right? They're just precise predictions of behavior and precise descriptions of how restrictive your model is, okay? Now, using these restrictions, you can actually verify it on data. And if data miraculously passes all of this, you know, then you have yourself a model akin to physics, right? But if it doesn't, then go back to the design board. So we're still on back to the design board. What is the nice thing about this? Well, actually, we know when we have to go back to the design board. Don't you agree? That's great. That's the whole point about science, right? So you do a model, you try to simplify it as much as you can. You derive the empirical implication. You go to the data tells you no. So it's not symmetric. It's negative semi-definite, but it's not symmetric. Go back to your design board, okay? But now you know you have to go back. And now you know what feature you want to remove, okay? What is the bug? So you go back and you try to change it. And by changing it, you hope to get a new model that doesn't imply symmetry, but it still gives you negative semi-definiteness. And it still is somewhat tractable, okay? It still is low dimension. And so have people been doing this? Well, we're doing it right now. So there are many candidates of alternatives to this original model, okay? And, you know, which one is gonna win? Up to the data, right? But this is the approach of modeling demand. Now, I'm gonna tell you what economists did in the 90s, including Deaton, Angus Deaton, the Nobel Prize. And they did something that is no longer well seen. So I'm going to tell you so you don't do it, because people are still doing it. And it's just imposing the properties in a blind way, okay? So what I'm telling you is this. So imagine you're in the 90s and you don't have Amazon data, right? You have really, really crappy data from national accounts. Aggregated data that is mismeasured, is really noisy. You don't even have real goods. You have just groups of goods. So you have food versus clothing versus transportation. These are not even real goods, right? So nobody buys clothing. They buy a t-shirt, right? So all of these issues happen there, and you're given this data, which is, you know, the typical data you have in the 90s. Okay? Now, you still have prices, what are prices of these imaginary bundles? Well, these imaginary bundles don't have real prices. They have price indexes, right? So the CPI, the Consumer Price Index. You have seen this, right? So anytime you have checked anything about the inflation, this is done with CPI, right? So CPI is just done with a basket of goods with certain weights, and they do a weighted average of prices, of real prices. They average it in a very, you know, arbitrary way. Well, they think about it, but it's really arbitrary. And then you get this price index, you know, which is a number between 0 and 100, okay? And so this is your data in the 90s, okay? And then you estimate a demand, such as the one I told you, right? So XL equal to a function of prices, okay? And then you estimate a Zlotowski matrix of it, and it happens to be non-symmetric and non-negative semi-definite. So you're Angus Deaton. What do? You say with this very bad data, very crappy data, utility maximization, which is the workhorse, the heart of any theory that we have so far seen in econ, is wrong? Can you say that? I wouldn't have the courage to say that, right? The data is so bad that, you know, you cannot really claim that this is a violation of the utility maximization. The data is just not there. So what people in the 90s said was this, which is not scientific. They said, look, why not do we believe our theories instead of the data? And let's just impose the restrictions. So I estimate now demand imposing that Slotski, so it's the closest demand, the closest model to the data, such that the Slotski matrix is negative semi-definite and symmetric. Do you understand what I'm saying? So this is a restricted model, right? And this is what was called a structural modeling. And the idea is that because, you know, utility is written in stone, you can just impose it to the data, and then this will avoid bias of measurement error and all other noises of this very crappy data. So what does it mean in short? For the people in the 90s, theory was above data. Did it make sense for them? Maybe, right? Because data was so bad, right, that why bother, right? Just impose the theory. It makes sense at least, right? So, but now, will you have the courage to do that? No, right? Like, if you are trying to be higher in the private sector, everyone will laugh at you. So don't do that. Don't be that economist, right? So data is first. That's the reality, right? So you have high quality data now. Yeah, you may have some measurement error issues as well, but you have to model it appropriately using statistical tools for that. But don't go and restrict a theory that nobody has verified, right? So we're not talking about here about a general relativity, right? It's a theory that we still don't know whether it's correct, okay? So the point here is that right now, right, the way to do it will be, let's estimate this model in the most general way, and let's try to see whether the simpler, the low dimension utility maximization model explains the data as good as the fully general model. And if it does, actually it's amazing, because that means the simple data that can make good predictions actually does as good as a job as the more general model, okay? And you see that there is a continuum of models, right? Full machine learning, fully non-parametric makes no predictions, but will fit any model. Utility maximization is maybe too restrictive, but will make excellent predictions. Precise predictions, maybe completely wrong, right? And now, of course, the game of new modelers is something in the middle, right? So something that relaxes utility maximization enough to be flexible enough, you see? But at the same time, you know, don't get to the level of machine learning, which is completely empty of prediction, okay? Okay, and in between now for the practical minds here, you can imagine easily that machine learning is still useful if I combine it with my utility maximization paradigm, right? So right now I wrote in my board something very simple, and let's go back to that one. Let's go back to that one. I wrote this with a quadratic model, right? But why does it have to be quadratic, right? Maybe quadratic is too small, right? Maybe the full indirect utility is completely high dimension, right? So it can be a fully non-parametric object. So then I can use machine learning for that, right? So I write down an indirect utility that is a non-parametric function of prices, and then I use lasso there, right, to be able to select from these multiple coefficients to see which ones are the better ones, okay? So I use model selection there. And then, of course, I can include then cubic terms to the power of 4, to the power of 5, and so on, fully general one. And then, you know, I have a fully non-parametric modeling of demand using utility maximization. But even if you go fully machine learning there, you will still get symmetric Slotski matrices, right? So you can never get away from it, and that's your restriction. Okay, so short story, that's how you can use these things, right? And now, okay, so that's the first use. So you say you're trying to compete with machine learning guys. in their own terms. So maybe that's not the best idea. So what is the other advantage for you economists in terms with respect to machine learning guys? Well, machine learning guys cannot do something called welfare analysis, okay? So what is the other advantage of having a theory and a theory of welfare? That you can actually answer the following question. You can say, what happens, for instance, if I change a price of a certain level to a new price level? What will happen in terms of welfare of consumers, okay? So imagine that you are a guy in Amazon and you say, look, I want to earn more money, but also I care about consumer satisfaction and consumer loyalty, okay? So I want to know if I change this much amount of price, so I increase the price of toilet paper, which is the hot item now, what it was. And then, I change it, I want to get more money because of it. I want to understand elasticity. Okay, that's cool. I can put it in my pricing function and then maximize my profits. But at the same time, dynamically, I know that people that are not happy about the price change, their welfare decreases. And now they possibly can leave Amazon, right? They say, I don't buy in Amazon anymore, right? So maybe I want an estimate of welfare, okay? Okay, that's for Amazon, but it becomes even more important if you are working for the government, right? So the government does not maximize profits, of course. Well, at least, at least formally. And then what do you do? So what is the objective of the government, at least? Well, you will hope that trying to maximize welfare in some sense, right? You're not fully utilitarian, you're not maximizing the sum of welfare, right? But you still try to make things better off, okay? So then you have to do a welfare analysis, okay? So using just machine learning is very hard to do welfare analysis, except if you have an enhanced data. So you ask them also how they feel. You say, you pay $10, do you feel happy? I mean, this is the frontier, right? Maybe asking them consumers directly how they feel is a way to understand welfare. But remember, all this theory in econ was developed when you didn't have that freedom of collecting any data you have, okay? So we're trying to restrict our data to the very simple price and consumption data. And then using only that data, we're gonna ask about welfare, okay? Do you understand? So now welfare analysis is gonna be the comparison of what will be the utility level that you achieve when you start from a starting point of P0, original price, and then you change to a new price, P1. Okay, and in order to do this, we're gonna try to measure this in monetary terms. So what is the issue with utility? Well, the issue with utility is that it's measuring utils, right? So utils are utils of Tyson or utils of Victor or utils of Alexis. So each of them is a subjective measure, right? So you cannot compare them. What you can compare in principle is money, okay? So what you can do is use this money metric utility function. So what is a money metric utility function? Is take a utility value, put it inside the expenditure function, and then the expenditure function is measured in monetary terms. In what particular monetary terms is in terms of the price of reference, okay? So imagine you have access to the expenditure function, so you estimated it. And then you know the expenditure function for the reference price, which is the price at some time period, so say 2019, okay? This is the regime. So price of reference is 2019 prices. So now you put any value of utility inside it, and this is gonna give you out a money amount of how much will you spend to reach that particular level of welfare, okay? So now, the comparison I'm gonna do now is in terms of money. So I'm gonna tell you how much money metric utils, right? So how much money do you have by achieving utility one with respect to the reference price PREF with respect to this original welfare situation. So now you have some U0 connected to the original price, and you have U1 connected to the second price. Now you evaluate the changes in terms of the money metric. Do you understand? So I'm not comparing the indirect utility directly. I pass it through the expenditure, and now I can compare the money metric, okay? Got it? And I'm gonna do the same for, so this is equivalent, right? So if I replace the indirect utility here, And now I can see that this is for a fixed income, price initial P0 to P1, okay? And the expression will be positive when it takes more well to achieve U1 at prices P rep than to achieve U0. So the difference is measured in dollar terms. And this is called often, as I said, a money metric indirect utility. So now, changing the reference point, I can construct different measures, right? So the first more famous one is what's called equivalent variation. And this is measured at the origin reference price. So if you have an initial situation P0 and a new situation P1, basically you fix the reference price as P0. So in that case, the equivalent variation is the amount of money the consumer is willing to pay. So this is the key word, willing to pay, to avoid a price change, okay? So this is a measure of, you have this price which is multidimensional. It's a huge vector of 100 entries, right? So you have this price, initial price vector, they have the new price vector, this changes, for instance, Amazon just increases toilet paper and you know, bread making ingredients, and you know, and with respect to not changing the rest. And the second change is I'm gonna increase 1 cent in all goods instead of just increasing toilet paper and bread. So which one of those price changes is better? Do you understand that ranking them is not easy? You have 100 vector entry, a vector of 100 entries, right? And then you have two different regimes of price change. Maybe they give you the same income in terms of the firm, Amazon, but you don't know which one is better in terms of the consumer, right? So this can answer that. So this will tell you this price change is better than the other, right? So if you go from the initial situation to the changes in the two goods versus the initial situation versus the tax over all possible 100 goods of a cent, okay?
Are we looking at this in terms of welfare still, or just in terms of?
It's in terms of money, and is the amount of money the fixed individual will require to achieve this level of welfare, okay? So again, this is not among consumers. This is for a fixed consumer, okay? And the compensated variation is instead, is now changing the reference price to the endpoint P1, okay? And so the compensated variation answers the question of how much must I compensate you, so I, the economist, to you, the decision maker, to make you as well off as before the price change, okay? So the idea is that in this case, this is about willing to receive money instead of willingness to pay, okay? So what measure is better? So it depends on the question, right? And also you can use other reference points. So that's up to you. And I have some reflections on this, and then we're done with the class. So imagine, for instance, that you have the city of Los Angeles decides to build a new freeway which cuts through a neighborhood, right? How much would the city have to pay the residents of this neighborhood to keep them as well off as before, right? And then this question will be better answered by the compensated variation, right? Because the city will have to pay them, okay? So this is the typical question for the government paying you because they're gonna take out your property, part of it. And then what is the most residents will pay to not have the freeway? So can you allow the residents to pay you a tax and say, look, we don't want the freeway through this part, we're willing to pay a higher property tax. So you can do a freeway that is more expensive elsewhere, okay? And this is the equivalent variation, okay? Now, I have a question for you. So now that we can collect data freely, what prevents me to just go in Los Angeles or here in London and run a survey, online survey, and ask all residents, right? You know, are you willing? So do you want, how much will you pay for not having as we have in London here, the train going through the city, through the middle of the city, right? So how much will you be willing to pay if you're in downtown to avoid the hassle of waiting almost half an hour when you want to get for a coffee, right? So how much will you be willing to pay? Why is not that not an option here? So why can't I just ask them directly for the equivalent variation or the willingness to pay? And the same for the willingness to accept, right? So if I'm willing to buy something that is controversial or bad, so say I want to buy, to build a nuclear plant, and I'm putting it on the outskirts of London, right? And then I go to this certain suburb and I ask them, okay, I want to put this here. How much are you willing to receive in order to accept this location being moved here? This plant, this nuclear plant being moved here. Why can't just survey them, ask them? So anyone has an idea? What do you think, in other words, rephrasing the question, which one do you think is better? So you are now working for the government, you're in charge of this, right? You graduated as a PhD of econ, and this is your first job, right? So then what would you do? Would you estimate some demand and then compute this composite variation, equator variation, or would you do a survey and ask them directly? Okay.
I think maybe it's hard to, it wouldn't be good to do the survey just because like maybe there's no benchmark. So it's like, how do you even have an idea of like what you're willing to take or what you're willing to pay if there's not really anything to compare it to?
Okay, that's a great point, right? For instance, imagine that, and this is what happens, in developing countries, right? So a lot of the developed countries send their garbage to low-income countries, right? And then they pay them somehow, right? And they pay usually politicians, but say that they ask someone, right? How much are you willing to accept? Most people don't know what kind of trash they are sending, right? Maybe they are sending something that's really, really bad that causes cancer, but I don't have that information. So, if you don't have information to actually know, your willingness to accept or willingness to take, to pay, then how a survey will be useful, right? So in a sense, you actually need full information to answer correctly. Another possible concern is that people may lie, right? For instance, you say, okay, I want to build a freeway through this very rich neighborhood, Sunningdale. Here is the fancy neighborhood in London. So I want to build a freeway. So I'm gonna ask them, how much are you willing to take as monetary compensation, you guys, in order for me to pass the freeway through the middle of Sunningdale? And now it's a law, you have to tell me an amount. They're rich people, they have a lot of bargaining power, right? And they can wait and delay it as much as they can. So they're gonna ask the most they can, even above their actual willingness to pay. So how do you elicit even in a way that reveals the minimum? So if you are the government, you want to elicit the minimal amount people will take to let the freeway go, okay? Actually, I'm gonna give you a better example for our COVID times. So, that in developing countries, such as my home country, Ecuador, an issue is that when people are required to quarantine because they tested positive, right, is that they may not have the resources to actually be at home, right? So then, kind of immediate policies to give them cash transfer, a conditional cash transfer. So I'm gonna give you this amount of money so you can stay 15 days at home, and this will cover your basic needs, okay? Now, how do I elicit this amount? So this is a question I had to face some months ago, right? And how do you do it? So this is exactly this question, right? So willingness to accept. So one way to do it, right, is to estimate demand function of basic needs. You can do this because there is data on consumption of food, right? So you do this, you see how much people usually spend on an average consumption basket that delivers them enough calories to survive. And actually not only enough, actually twice the threshold of calorie consumption that the UN predicts and so on. So you can do this in kind of pseudo objective thing. So you can estimate this demand function and then estimate, what will be the amount that people need, okay? And then when we measure this for the case of Ecuador, for the case of actually 2 weeks, it was actually, the amount was $30 US, okay? Using the structural procedure, so estimating a demand. Later, we had the opportunity to run a survey. So we did a survey for people in different levels of income, right? So for the people that are poor, we use phone calls. And for the people in the middle class, we use email, okay? And then for them, we actually ask them, okay? So we tell them, look, how much are you willing to accept in order to stay at home, you know? If you have to be forced to stay, right? So if you get out of home, you lose the cash transfer. Okay, that's the deal. So in order to make that question, actually, you have to run it as a protocol that is actually starting for a simple question. And you start with saying, with low value. So you cannot ask them to just give you a number. So you have to tell them, will you take, for instance, $10 and then for to be have pretty much be tracked to stay at home. And if you lose, you go out of home, you lose it, right? And then if they say yes, then you stop the question, right? This is an online or by phone, so it's interactive. So if they say I will take the 10, you stop there, right? And then if they say I won't take it, it's not enough, then you offer them the next tier. You say, okay, so can you take now 20? Okay, and if they say no, you offer them the next one. Okay, so few people realize they actually have the option of increasing it a bit, right? So eventually they say yes, and this is the lowest amount that they will take. Okay, and this is called the multiple list technique. So for instance, for Eduardo, so yeah, usually you can do this with these techniques which are incentive compatible. So if you ask them in a certain way, you can actually ask them, get some more meaningful answers. Okay. So yeah, and then when we compute the value, you know, the average value was actually very close. So to the value we computed the other way. Now, of course, we get a lot of heterogeneity, and that's the interesting thing, right? So if you estimate this with demands and the statistics, usually you don't get the detail to be able to estimate individual willingness to pay. So we get kind of willingness to accept. We get usually average willingness to accept. So now when we do the survey, we actually get individual reports, okay? And one surprising thing was that information is important, as Eduardo mentioned, right? So it turns out that people that thought that they didn't have any risk of getting COVID, and they didn't, and even if they get COVID, they thought nothing was going to happen to them. You know, they actually were requiring a lot more money. That's reasonable, you know, but maybe they have an unreasonable belief. Do you understand? Right? So they just think COVID is fake. What we also found, and this is, you know, more out of curiosity for you, is that people that are fatalists, they actually were also they also wanted a lot of money. So people that basically believe that they will get COVID for sure, and if they get it, they will end up in ICU, they actually were more likely to also require more money. Okay. And why this happens? Well, it's kind of weird, and so in our paper, we didn't have exogenous variation to understand exactly why that was happening. But there was a different paper in Sweden where they actually did something similar in a parallel way to us, where they actually tried to randomize information about COVID to households. So that means some households receive at random in an experiment information about how bad is actually COVID, given your age, gender, and current existing conditions. And when people found out about more objective probabilities of how risky this is, and also about probabilities of getting COVID in your particular location, given the average rates of infection, then people actually behave more moderately, and they actually were willing to take less amount of money. Because what happens is, if you go to the extreme case, people become irrational in the sense that they just want out because they know everything is doomed, and why bother, right? So that's kind of the explanation they give in this Swedish paper, where they actually find that by randomizing information. So when they give good quality information and people improve their information, then they start becoming more moderate in terms of their behavior. So for us, we observed the same phenomenon, but we didn't have the causal explanation. So the short story is that, so no method is perfect, and usually you have to use both. And both have caveats, right? So usually the issue with this structural approach is that, of course, you're assuming that people are rational, but even passing that thing is that usually data will allow only you to get average quantities, right? And also they will be sometimes imprecise. So just hard to compute. While direct measures, even if they can be improved by question techniques and that are incentive compatible and good design of surveys, and they will give you a lot of heterogeneity, and they will give you a lot of richness in terms of what you're getting. But at the same time, they actually depend on information that people have, right? For instance, in a way, the survey, the willingness to pay, was underestimated because we have a lot of people that were over-optimistic about COVID or were over-pessimistic. And these people were not being rational, right? So we got this weird belief distribution where you have these big bins at 0 risk, at 1 risk, right? And both of them are behaving in ways that are not rational. So you cannot really think about them as behaving consistent with utility maximization. Okay, so this is just as a peel of what you have to do as an economist, right? but the real, message is that this is our comparative advantage, right? So welfare analysis, this is not done by machine learning guys yet, and they don't have the tools, right? So basically, this is what we do. That's why still economists have jobs. So bear that in mind, and also when building your tool set, this is the things you have to specialize on, right? So trying to do this analysis, or trying to do welfare analysis, structural analysis, and modeling, okay? So with this we're done. What is the plan? So right now, I give you some additional material that you can check in the break, at least for me. I know you have other classes, so no need, it's not an assignment. But the one I suggest, especially for people having issues with the math part, is that there is this, you Google it, is Matrix Cookbook Notes Online. So it changes the website. So I just stopped bothering putting the link because it's gonna get broken. But if you Google it, right, the Matrix Cookbook, and this has this, shortcut to matrix derivatives. So of course, this is, a good refresher. I'm not gonna test you on this. And another good resource for a good treatment of math, especially the first chapters, is the real analysis for economists. So this is more advanced. The other ones, I guess, already. So this is the Simon and Bloom, all these other typical books. Those are good when you want to understand the simple math, but for Mascolel, I think is the first chapters of this real analysis for economists of FAO are better. Then the later chapters are too advanced, but you will know this easily. Then also notes that are not mine, but I also use them somehow, and then, sometimes are better in some dimensions, is the online notes about general equilibrium by David Levine. So this is basically for the second part of the course. And Nolan Miller has really good notes on the first part. So these are very simplified. The summary is based a lot on him, but the main course is based on Mascolel, so it's gonna change. But this is useful for you. So the book, Mascolel, Whiston, and Green. So get it in whatever format you want, right? Mascolel, Whiston, and Green has a mathematical appendix. It's short and to the point. I think it's worth reading it just to refresh. So that for sure do that. And there is other books that, these ones I don't use at all, but maybe you need some extra books if you want to understand a concept. So personally, sometimes if I understand something, even beyond talking to everyone, reading, sometimes a good resource is another book. And sometimes the take in that book is very different and helps you to understand, okay? So the books there is Jelly and Rennie, and the Krebs book. Those are really good, but I'm not gonna use them at all. So this is mostly for you, right? So in summary, the basic thing you need is the micro theory, Mascolel, Whiston, Green, my notes, and that's it, right? The rest are things you can do optionally, okay? And then we're gonna do this, so Friday, so tomorrow, I'm gonna do just the second problem set. So we're gonna do it kind of in class directed. So I'm just gonna upload it before the class, and then we're gonna work pretty much in groups. I have to finish one thing. So there is this example in chapter 2 about ramen noodles and how to model Giffen goods. So I'm gonna go over that before the first part of the class, and then the rest of the class is gonna be kind of problem solving. And yeah, also I will be taking questions and so on about the main course, and we're gonna figure out, I'm gonna give you also the preview of the syllabus for the main class, okay? But tomorrow. So today we're done, okay? So right now, you're free to go, but if you have questions, I'm gonna be here for 10 more minutes. So thanks. I'm gonna end the recording right now.